the hard potential of the nuclear force kicks in, the protoneutron star stops collapsing. This drives a shock wave heading outwards. The shock wave in all models stalls, and it stalls due to a combination of energy losses from destroying previously existing nuclei, neutrinos, and it is held inwards by the ram pressure of the infalling material. And the problem for the last 30 or 40 years has been, how do you revive that shock wave and have it start to expand outwards? Because unless you can revive that shock wave, if you can get it to start going outwards, it will propagate through the rest of the star and you will have a supernova. If you cannot revive that shock wave, it will not. And so depending on what you want to have, you can have some combination of neutrino heating, turbulence in the region between the protoneutron star and the shock. Instabilities in the shock may drive you to an explosion, in which case you'll get a supernova. You will end up with a neutron star if then basically all of the mass outside gets thrown out. If some of that mass falls back on, if you exceed the Chandrasekhar limit of the neutron star, it will collapse to form a black hole. Okay, and so this process is called the question of how much fallback mass there is. If the shock doesn't revive, you have a failed supernova or a black hole. Now, I was tempted to actually bring a star, or at least a ball, and hand it to Adam Burrows, who unfortunately isn't here, and ask him to blow up my star. Now, the problem is, first of all, he's not here to tease. At least I don't see him. But the second thing is, well, it's hard to put a basketball in your luggage. So here's what you know about sort of this process. And this is due to many groups, of course, including Adam. So the first thing to be slightly aware of is that no one blows up stars that are below about 10 or 11 solar masses. Those represent about 1/3 of all core collapses, and they are never simulated. The reason they are never simulated is that no one can evolve the star to the point where they collapse. Okay? The lower mass stars, around sort of the very lowest mass they actually do simulate, those can relatively robustly explode. Okay? If you go to higher mass stars above 12, they do not blow up in 1D. Is that if you hand someone a basketball and say, please blow up my star, and you say you have to do it in spherical symmetry, they really do not blow up. If you go to 2D, there was great hope, because in 2D, suddenly they became much easier to explode, in part due to the development of very large-scale sloshing motions in the region around the protoneutron star, which would then help to prompt the explosion. Problem, of course, is that cascade to very large-scale turbulence is a characteristic of 2D. And so when you go to 3D, suddenly it doesn't really want to do that anymore. And so the current state is lots of people are trying to do explosions in 3 dimensions. Sometimes they explode, and sometimes they don't explode. And the issues they are worried about is there are questions of the details of neutrino physics and transport. There are questions about the cooling of the protoneutron star, sort of exactly what neutrino opacities are under these conditions, for example. There's the question of how well you can resolve or deal with the turbulence between the protoneutron star and the shock. There are questions of the instabilities in the shock. There's a question of exactly what state you put the progenitor in. What is the rotation of the core? And increasingly, people are worried about the fact that if you go and look at actual 3D simulations of the later phases of the nuclear burning, spherical symmetry is not really the case, is that you can have quite complicated interactions between the inner few shells of nuclear burning. And so you may have quite complicated mixing and even velocities, non-simple rotational velocities in the regions where you have the outermost shells. And all of these are problems. And arguably, some of them may well be imponderable, is that you can make a particular set of assumptions, but for example, it will be very hard to ever know what the core rotation of these stars is. You can sort of do this in some cases with Kepler, maybe, that there's some stars where you can get sort of couplings between the G and P modes and can learn something about the rotation of the core. But otherwise, unless you think there's going to be a revolution in understanding angular momentum transport in stars in the near future, some of these are just going to be things you put into the simulations. And so one problem is that you have all of these people trying to blow up stars. And if you go and talk to them, their goal is to make every last star blow up. But the question is, what is their basis for thinking that? Okay? How do they know if I hand you a 20 solar mass star, right? Do they know whether the correct outcome is an explosion or not an explosion? And this is, I would say, an experimental question or an observational question, since we're doing astronomy. And so first I want to talk about basically some mostly observational arguments for why there really should be a population of stars which undergo core collapse. That does seem to be inevitable, but likely don't explode. So the first thing you might worry about is just where you might want to worry about this happening. And so while they can't robustly tell you whether the star is going to explode or not, they do have a handle on the explodability of stars. And there are a series of recent studies by this, including one by Andre as part of his thesis. And to simplify somewhat is outside of the core of the star, depending on the nature of the progenitor, you have different density distributions. Okay? As you are trying to revive the shock, the density distribution in that region determines the ram pressure that is trying to keep the shock from exploding. So if you have a progenitor structure where the ram pressure is higher, it is harder to explode. If you have a density structure in which the ram pressure is lowered, it becomes easier to explode, no matter what you think the physics of reviving the shock is. Okay? And so you ought to be able to say something about the explodability of a star, even if you can't say exactly where you should put the threshold for where you want to go, one or the other. A way of characterizing this, which gets the first order answer, is just the compactness. And it's just you go to some mass cut, say where the enclosed mass is 2.5 solar masses, and look at the ratio, rescaled to be dimensionless in ways I'm not going to worry about defining. Look at the ratio between the enclosed mass and the radius of that enclosed mass. And that is a way of characterizing essentially the degree to which you're going to have a ram pressure holding the shock in right after the formation of the protoneutron star. It is an oversimplification, and at second order there are other effects, but this captures a lot of the effects. All right, so here for a series of progenitors is what this compactness looks like. Okay, so here's the progenitor mass, and it starts at 12. This is the progenitor just before the core collapses. Just before the core collapses. Okay, so this runs from, the scale doesn't right work, it runs from 11. So the first thing to keep in mind is that if the minimum mass for a supernova is around 8, which it seems to be, 36% of all core collapses are off the left side of this plot because no one can run those progenitors. Okay? So then we start at 12. Okay? The 12 solar mass stars at the end of their lives are red supergiants. Basically, they have a compact helium core with a very, very low density hydrogen envelope around them. And so basically is if you can get a shock through the core, they're very easy to explode. Okay? And so these low mass, 11 or 12 solar mass progenitors are quite easy to explode. They have very low compactness. Okay? Then as you head towards 15, the compactness rises quite rapidly. Okay? There is a lot of complex structure as you head in towards 15 or 20 solar masses. That is evidently all real if you believe Stan Woosley. And the reason is the exact structure of the core at that time depends very sensitively on interactions between the carbon and oxygen burning shells. And so very small changes in the mass can lead to quite different levels of compactness of the star when you explode it. Okay? So this is not numerical noise. Woosley would say this is all real changes in the structure as it goes to explode. You get to 20 or 25 solar masses, and you get a huge increase in the compactness. Okay? Then it goes down again. You get another spike around 40. And then what you're starting to see is this is telling you something about how many progenitors are available. So the reason it has only discrete points is that's the sampling of progenitors that are available. Okay? So these are easier. Those are harder. And just again, to keep track of where things are is, so we have about 36% are down here. If you go from 11 to 15, that's about a quarter of all core collapses. If you go from 15 to 20, that's about 14% of core collapses. If you go from 20 to 25, that's about 8% of core collapses. So if you just say that everything below about 15 collapses, that's 60% of all core collapses already. Okay? So about 60% of all core collapses lie in this easy regime. And so the question really is what happens to the other 40%? Well, this is something we have to experimentally determine. I will come and draw a dotted line, and it will be at about 0.2. Okay. I haven't yet justified that statement. All I've said is it becomes harder as that number becomes bigger. Andre has tried to justify that as one of these papers. And here and there sort of models of the explodability of stars for certain criteria which makes sense for matching 87A and various other criteria. Here is progenitor mass and then what you get out. So gray are things that undergo a failed supernova and become black holes without an explosion. Blue are things which explode. And so here you can see this island of around 15, it's hard. Some of these other islands are as you approach 20, which are hard. A higher density of things between 20 and 25 that are hard to explode. And then a smattering out here. And you can again see the problem that there are only isolated samplings of the progenitors. So these are a study of stellar explodability. They aren't actually numerical simulations per se. Andre can give his talk on his method. Yeah. So these are non-rotating. This case is solar metallicity. If you look in his paper, they do look at lower metallicity progenitors. You know, in some sense, the part of the problem is people look at progenitors which are either solar metallicity or basically no metallicity. There's not much point in looking at no metallicity cases in the present day universe because all the stars we see explode are solar metallicity. But they don't run, no one runs those progenitors. So a problem for these studies is a dearth of progenitors. So then the difference between the orange dot is basically the binding energy of the envelope of the star. The blue plus red is an estimate of the energy you'll get in the explosion. So basically this difference corresponds to the energetics of the explosion. And so you can see at these lower mass things you'll get quite energetic explosions. As you approach these high compactness 15 solar mass explosions, you get less and less energetic explosions. And parsed in between, you can get different ranges of the energy of the explosions. Okay? But the question really is, you know, this is an estimate of how much of this is gray, meaning failed supernovae. If we change the assumptions about the explodability of the stars, we would get different bands of gray. And the question is which set of the bands of gray is correct? Okay, so a way to determine this is you simply want to work out the mapping between the progenitor stars and the outcomes. Right? Is if I can find all of the outcomes, failed supernovae and successful supernovae, go back and look and see which star explode, then in theory I can make that mapping. Now, one thing you have to describe the supernova you get out is basically the supernova type. Okay, and so there's this long lexicon of supernova types, which basically corresponds to a sequence of mass loss. Okay, so the most common supernova are called type 2 or plateau supernovae, and they correspond to, at least it's believed, red supergiants with still a lot of hydrogen in their envelopes. Okay, so they're characterized by spectra with hydrogen lines. You can have peculiar versions of them. An example of a peculiar version is SN 1987A, which had a lot of hydrogen but exploded as a blue supergiant rather than a red supergiant. Okay. Then you go to 2Ls. Those are believed to be things where you say have a tenth or 2/10 of a solar mass of hydrogen left in the envelope. So most of the hydrogen envelope is gone. You have 2Bs where you're down to hundredths of a solar mass of hydrogen left on top of a helium core. Then you have 1Bs where you see, 2Bs where it transitions from, first looks like a spectrum with hydrogen and then all the hydrogen goes away. 1Bs have no hydrogen. 1Cs have no helium, although the absence of helium lines does not mean an absence of helium, it turns out. And then 2Ns show narrow hydrogen emission lines, and that's an indicator that you have a dense circumstellar material around it. And what happens is you photoionize the circumstellar material, and that produces the narrow lines because it doesn't have the velocity width of a supernova. Okay? This, however, is not a sequence in the mass of the progenitor star. It's a sequence in how much mass I have lost. Okay? And first of all, mass loss is not a unique function of mass. Second problem is there's those things called binaries. Right? Almost all of the massive stars are in binaries. A very large fraction of the massive stars have interacted with their neighbors during their lifetimes. And so in most models of trying to spread these objects over the mass of the progenitors, it is not a unique sequence. It's not fully worked out, but here, for example, is an attempt by Nathan Smith to divvy this up. So basically, it's just a numbers game. Here is the initial mass. Here is, it's a little bit optically not correct, but here sort of is a distribution of objects you would get under a saltpeter IMF. And then he's just trying to divvy up the fractions of supernova they observed in the Lick supernova survey into mass bins. And so here you can make the 2P run from 8 to 22 solar masses. You make the 2L run in this bin around 30. You make the 2N run out here. And then you make all the 1BCs basically due to binary stripping. Okay? And if you go and look at this paper, they have like 8 different variants of how you can try to split up these supernova types across mass, depending on what assumptions you want to make about how much you want to assign to binaries. This is just based purely on numerology.
I agree, but if you ignore the fact that 1 billion produce more energy factor 10 and more nickel factor 10,
well, but at least,
it doesn't sound
but at least,
it's just the difference in the angle of damage.
but at least in these models, not only Andre's, but all of these explodability models, the amount of nickel you produce is not a monotonic function of mass either.
But I'm saying 1 billion are not just the two pieces without hydrogen angle. This is observationally proved.
But not all 1BCs are stripped high mass stars, because that doesn't work out numerically. So if you really want to do the mapping from the mass of the star to the outcome of the star, you really have to go and find the star which exploded. And so this is the search for the actual progenitors. And this is dominated by two groups, one led by Stefan Smart at Belfast, and one largely led by Van Dyck and Filipenko's group. And the fundamental problem is this is very hard. You can only do this even with HST data at distances of 20 or 30 megaparsecs. If you're doing it at 20 or 30 megaparsecs, it also depends on the existence of HST data, and the fractional area of all galaxies within 20 or 30 megaparsecs that has good multiband HST data is small, because HST has no field of view, and these galaxies are relatively big. And so as a result, there are only about 10 supernova progenitors, that's being somewhat generous, that have even decent two-band photometry. Okay? There are many more which have limits. And the other thing to keep in mind is this will never give you mass resolution at the level of a half a solar mass or 1 solar mass. In the final analysis, what you're going to do is you're going to get an estimate of the luminosity of the star, right? And you're going to turn the luminosity of the star through someone's stellar evolution model into an estimate of the mass of the progenitor star. Okay? And that's never going to be believable at the level of less than a few solar masses. Okay? The first thing is when we realized when we started getting into this is if you took all of the available data on progenitors at the time and you compared it to what you would expect for a saltpeter IMF, is there just didn't seem to be any high mass progenitors. There seemed to be a deficit of high mass progenitors. And this was quantified much better by Smart's group for the type 2p supernova. And basically what they found is that the red supergiants all correspond to stars between about 8 and 17 solar masses, whereas all standard stellar evolution models would have that stars should be dying as red supergiants up to 25 or even 30 solar masses. And you'll come back to that, this is not, this depends on what you think about stellar evolution, but let's just take that as what the standard line was. And so here's the sort of thing which they could do. This is updated from his recent review article. And so here is their estimate of the progenitor mass. And here are all of the limits they think they can set, or measurements they can set on the mass of the progenitors. These are all these type 2p supernovas, so red supergiants as the progenitors. And the point they make is, well, here is kind of the distribution they see with the upper limits. Here is the distribution they should have seen if, say, red supergiants exploded up to 30 solar masses. And so their point is, this curve is missing this region, and so you seem to have a deficit of red supergiants as supernova progenitors. And so in the formal limits, what they have is things between about 8 and 17 are exploding as red supergiants. At least from the stellar models they were comparing to, you expected it to run from 8 to 25 or maybe a little bit more. And that deficit corresponds to 10 to 30% of core collapses, depending on exactly where you are on the limits and where you think the minimum mass and the maximum mass for supernova sit.
But this again comes from assuming 1 billion nuances are infinite.
No, all this assumes is that stars less massive than 25 solar masses explode as red supergiants. It doesn't. Anyway, yeah, I would say it doesn't, but.
Can you explain so what exactly goes into the assumption of this strong upper limit?
It's basically luminosity. It's basically, you can set a firm upper limit on the luminosity. In this mass range, if they were red supergiants, the luminosity rises very rapidly with mass. And so it's just that L is going as m to whatever power it is in the models. And so if you can set a limit on the luminosity, and you think you know the temperature because it's supposed to be a red supergiant, then it can't be more massive than something. So.
What's the problem that there are a number of blue, yellow, and red supergiants wasn't right?
Right.
Is that problem still there?
I think in newer models and with Massey's newer survey data, I believe it is less of an issue. Okay, I think it has not completely gone away. But I think it is not as severe as it used to be. Right. And averaging over the various claims about A7A, I would say that the people in favor of a binary, doing that with binaries probably win. But, okay. Okay, so there are escapes from this. And the simplest one is you just change stellar evolution, or the equivalent to, say, playing with binaries. And you simply say is that, the reason is because you simply change the mass range that is associated with blowing up as a red supergiant. And so, for example, Groh et al., which is the Geneva group of stellar evolution people, have some recent models in which they play with the angular momentum profiles of the stars, the rotation rates, and the mass loss. And they can drive Wolf-Rayet star formation down to as low as 17 or 18 solar masses. Okay. Now, Mark Pinsonow would then say the problem is those models are completely inconsistent with Kepler astroseismology, which I trust Mark. So, the problem. Because they use the same physics at lower masses. So if it doesn't work at lower masses, why do they think it should work at higher masses? So that's one thing, is you can just change stellar evolution. Okay, or mass loss really is what you're playing with. Another possibility, which is advanced, is you could get the luminosity limits wrong if you severely underestimate extinction, and in particular not so much foreground extinction as circumstellar extinction. And so this was looked at by Walmswell and Eldridge. They kind of push the envelope quite a bit, and in the end I think they still can't really make this work. The other interesting thing is there's another route to this which depends much less on looking at the photometry of a particular star or your lack of photometry of a particular star, and sort of applies across the board. And that is a series of studies done by Julian Del Canton's group in which they take supernova remnants in nearby galaxies and look at these stellar populations near the supernova remnant. And so basically they try to take a little region near each supernova remnant and using the things they've applied to all their studies of local galaxies, try to estimate the star formation rates local to that supernova. And if you can estimate the star formation rate history near that supernova, you can estimate the mass of the remnant. And so they've done this for a series of things. And here is their version of basically the same plot. This is, again, progenitor mass, or sort of mass they get in the local region for the mass associated with the supernova remnant. Here is the distribution of masses they would get from the local stellar populations. And here, for example, is the distribution they should have seen if everything up to 30 solar masses was exploding. And so basically, if they look at the stellar populations local to supernova remnants, they also find that they just do not find young enough stellar populations near supernova remnants for the supernova remnants to be associated with very massive stars. Okay? And that's not independent of stellar evolution models, but it is, for example, independent of circumstellar dust. Okay? And if these models for stellar populations are wrong because they're matched to CMDs of clusters and things, you have, it's a little bit harder to get out of this by changing stellar evolution because the models are sort of validated, shall we say, against young clusters and things.
How did they get rid of F1A?
What did they do? They had a game I'm blanking on. I mean, it's basically, I'm forgetting exactly what they did right now. Okay, so that's one indicator, and I'm not gonna. I assume you must be Boaz. No, sorry. Okay, I apologize to whoever I'm supposed to apologize in that particular set. There are loopholes in this, all right. But if you take it at face value, you would say that 10 to 30% of core collapses failing are one way to explain these observations. The second thing you can go and look at is the black hole mass function, rather the compact remnant mass function. So there's been sort of a long-standing series of studies, starting with Charles Balin in 1998, and then by the Farrell Ozel is one group, and Vicky Calagara's group is another group, looking at the mass function of compact remnants. And so here is one version of this showing a whole bunch of neutron stars and a whole bunch of black holes. And the curious thing about this, which is what they've sort of been worried about, is the mass function of neutron stars is a very narrow distribution, around 1.4-ish, with a few outliers to a higher mass in particular. And then the black hole mass function basically is picking up around 5. So most of these tails down here can be explained as just that you have statistical uncertainties, and so you'll have a tail to lower masses. And so at least taken at face value, the compact remnant mass function seems to be a quasi-delta function of neutron stars, with a few exceptions to prove the rule, a gap between 2-ish and 5-ish solar masses, black holes mostly between 5 and 10, and then with a trickling of black holes to higher mass. Okay? And there are arguments. I mean, this is a very messy, the selection function for this are very messy, of course. And so there are arguments about sort of whether this is a real gap or a deep minimum, or even if you should just not even attempt this comparison because of, the binary selection effects make it impossible. But taken at face value, that's what you seem to see. Now, the first problem this creates is think about the problem of having almost all of the black holes whose masses lie between 5 and 10 solar masses. Even with mass loss, right? Most stars at death are more massive than 5 or 10 solar masses. Okay? If you really strip down a Wolf-Rayet star, you can get it down into that limit. But otherwise, it's very hard to have a star die at 5 solar masses. And so the traditional way you would have to explain this is in order to get a 6 solar mass black hole from whatever a 18 solar mass star at death, you have to have a successful explosion. All right? So you have to have a successful explosion, and then you have this thing called fallback, where the other 4 or 5 solar masses falls back onto the protoneutron star and leaves you with the black hole, and the remainder goes out, and you get a supernova with the remaining 10 or 12 solar masses. The problem with the idea of fallback is that in everyone's attempts to simulate it, there is no natural mass scale with fallback. And so if you look at people's attempts to look at black hole formation with a fallback, or basically the whole series of basically the sort of models that Stan Woosley does, where you explode stars with a piston or deposition of energy, is they don't produce any particular number for fallback. The amount of mass that falls back is a continuous distribution. And so if you attempt to make the remnant mass function using the process of fallback, you find you cannot produce a deep minimum in between the neutron stars and the black holes, because there's no natural mass scale associated with how much mass falls back. The other thing is that spike in the neutron star distribution says that at least there are an awful lot of explosions where you want almost no fallback. Right? Because you have most of the neutron stars are in a spike that's only whatever, 1/10 of the solar mass wide. And so that means that for the vast majority of neutron stars you actually find, you can only have 1/10 of the solar mass falling back. Whereas for the black holes, you have to have whatever, 4, 5, 6 solar masses falling back onto them. And so again, it's sort of this odd dichotomy between the two.
How do you know the neutron stars can come closer?
You're going to tell me about that. I've now remembered who you are. Or no.
But is there an evidence? Is there an evidence for this? It's all this type of relativistic binaries.
We have the neutron stars and supernova remnants.
But which are not this.
So, okay. But you promised to tell me about that when we talked. Okay. So an interesting thing was realized by Stan Woosley. It was realized by a guy named Nadezhin in 1980, and then sort of forgotten to everyone except Stan. That the envelopes of red supergiants are basically almost completely unbound. Right? In the limiting of a simple stellar model, the equation of state of the envelope of a red supergiant is 4/3. The binding energy of a 4/3 polytrope envelope is 0. Okay? And so to unbind the envelope of a red supergiant takes a negligible decrease in the potential energy. And so Nadezhin pointed out, just on sort of analytic grounds, is that if you have a failed supernova, before you form the black hole, you lose 1/10 or 2/10 of a solar mass of rest mass energy in the neutrinos. Okay? That drops the gravitational potential of the star enough that it triggers a shock wave going into the envelope of the star, which unbinds the envelope. Okay? And so in the failed supernova red supergiant, you don't end up with a black hole whose mass is that of the entire star. You end up with the mass of a black hole, which is the mass of the helium core. Okay? The hydrogen envelope then goes floating away. Okay? And so partially motivated by that, we had been pushing this idea of failed supernova. Stan, with his student Lovegrove, went and simulated this. And indeed, as if you take red supergiant progenitors and you do a quasi-realistic job of dropping the mass by the amount you lose in neutrinos, the hydrogen envelope does go wandering away. Okay? So failed supernova of red supergiants produce black holes with the mass of basically the helium core. failed supernova produced from Wolf-Rayet stars, again, they've already lost their hydrogen cores, so they produce a black hole with the mass of their helium core, or however much more they've been stripped. Okay? And so that means that failed supernova actually have a natural mass scale for black holes that is 5 or 10 solar masses and not the mass of the star at depth. And this really provides the first natural explanation of why you would have such a bifurcation between the mass of the neutron stars and the mass of the black holes. Is that if you make the neutron stars the results of successful explosions with no fallback, okay, which is what you need to explain their narrow mass distribution in this scenario, and the black holes out of failed supernova of whatever you want, okay, they will give you masses in the range of 5 to 10 with a smattering of tails to higher masses from things like if you had a failed supernova of 87A. Okay, if you have a blue supergiant, the hydrogen envelope is much more tightly bound, and you can't lose it in the process. Okay, it has to be a red supergiant because that's the only case where the envelope is so weakly bound that it can go floating away. And so we can put this back in the context of this compactness of the stars. So here's a mapping of the compactness of the stars into the expected mass of the black hole. Okay, if you assume the mass of the black hole is the helium core. Okay, so this is now the black hole mass, and just look at this panel. So here is the compactness of the star which would produce it. Okay, so at low masses, okay, you would produce a low mass black hole because the helium core is small, but the compactness is also very low. Okay, then as you go up, you get into these 15 or 20 solar mass stars, which have this high compactness. They produce black holes in the range of 5 to 10. Okay, then as you go higher and higher mass in the standard models, you start, as you get above 30 solar masses, they kick on the mass loss. And so as you go to higher masses, the mass of the star depth drops dramatically because they're going to make the highest mass stars Wolf-Rayet stars. And as you do that, you start coming back around. So the red curve is these are actually more massive progenitors which are more stripped by mass loss, and you start producing smaller black holes at death again because of the mass loss in going to being a Wolf-Rayet star. Okay? So this is the compactness as a function of black hole mass, and then this is the number of things you would get. So this would be, if I just turned everything into a black hole, this would then be the mass function you would predict. Okay? The spikes are actually real given the progenitor models people have. Okay? And here, for example, is a version of, say, Calogera's or Ozol's model for what they would do as a parametric model of the black hole mass function, given that data, is they would have a sharp cut on a little bit over 5 solar masses, and then a tail going to higher masses. So if I wanted to, say, match this mass function to, say, Calogera's parametric black hole mass function, well, I would just go up, and I would say, well, I'd want everything sort of above here in black hole mass to collapse. And, well, if I just kind of draw a line across at point 2, there's your point 2, I would get the black hole mass function I seem to observe. Okay? And then the bottom panels just show a different set of progenitor models, but more or less the same answer. Okay? And so you can try to do this more formally. You can try to include something about the complete mass-dependent completeness of the black hole mass function. And it turns out the result is pretty independent of what you assume about that. And so if you run through these models, if you have something like 20% of all core collapses fail at compactnesses more than about 0.2, you get these sorts of mass functions for the black holes. Okay? Statistically, they are as good or better models of the data you have on black holes than Calogera's parametric models. Okay? So taken at face value, you could explain the black hole mass function if you add error bars, something like the 10 to 30% of the most compact stars above 0.2-ish form black holes in failed supernova, where the mass of the black hole is the helium core, essentially. Okay, so that's sort of the second line of argument why you might want 10 to 30%. And again, you see it would like to prefer the most compact stars, although in this case it was constructed to do that. The third one, which of these, I mean, you might think these are all really iffy, but the third one, which is perhaps the most iffy, is that if you compare the star formation rates as a function of redshift to the supernova rates as a function of redshift, the star formation rate systematically lies above the supernova rate. And it's a safer comparison than you think, because first of all, remember, star formation rates, while everyone transforms them into the total mass of stars formed, all star formation rate indicators are massive star formation indicators. And then you just extrapolate to what happened at the low mass star based on IMF. But if you just compare star formation rate to supernova rate, you're really comparing apples to apples, because the star formation rate really was a massive star formation rate, not a total star formation rate. And so this from Horiyuchi et al. Is here are a series of measurements of supernova rate measurements versus redshift. Here are a series of star formation rates as a function of redshift. And basically, one lies above the other at all redshifts. And if you try to translate that into sort of supernova rates versus star formation rates per volume, here's the one for the supernova rate, the star formation rate. And then here are various things you could worry about for what you might do. So playing with the IMF shape would let you shift this by almost nothing. Right? That's just saying it was an apples-to-apples comparison. They're both massive stars. Okay? You could try to play with what you lost due to obscuration. That's a bigger effect. You could try to, basically, you can play with the lower mass limit for the core collapses. That can give you a significant correction. You could say that people...
If you change from 8 to...
I don't remember the exact numbers used. You could say that the supernova people are bad at finding supernova in small galaxies, which is actually true. We know that from our SN project. And so that would drive this up. There are a series of fainter than normal supernova transients, which much of the supernova community wants to say are not supernovae. If you say they're wrong and that many of them are just low energy supernovae, then you can drive it the other way. And so I would say this one has, of the three, this one has many, many more imponderables than the other two. But it gives you a third case where you would like to have a failed supernova rate of some tens of % or maybe even a little bit more. So how do you find failed supernovae? In an ideal world, we would live in a galaxy with a supernova rate of 1 per year. This would make our galaxy much more exciting, just in general. But of course, if you had a supernova rate of 1 per year, all of these neutrino experiments or advanced LIGO would be able to pick up these events. And if you had the neutrino signal at the sort of signal to noise you would get, or if you had the gravitational wave signal of a collapse in our galaxy, you could tell the difference between which was which pretty easily. Unfortunately, unless you have a particularly long-lived graduate student, the actual event rate for our galaxy is, for a failed supernova, it's in this range of 10 to 30% of core collapses, is something like 1 every 500 years. So that's not very promising. Another possibility which can set something, and it isn't quite there, and I didn't put on here, is Super Kamiokande and other things are on the edge of being able to measure the diffuse neutrino background. So basically, the total contribution from all supernovae through cosmic history with all the usual integrations over redshift to get the totals. If you can measure the diffuse neutrino background, then you can actually also set a pretty good constraint on the number of failed supernovae. That may be done in the next 5 or 10 years, and it partly depends on whether the Japanese decide to salt Kamiokande with gadolinium or not, which will greatly increase its sensitivity towards lower energy neutrinos. What we instead otherwise realized in 2008 was that you can search for failed supernovae in nearby galaxies without using neutrinos or gravity waves. And that is, in the final analysis, what happens in a failed supernova is you started with a 100,000 solar luminosity star, and you ended up without one. And so you can just go and look at nearby galaxies where you have enough sensitivity to find a 100,000 solar luminosity star and see if any vanish. And so now you get to run in a system where you have the supernova rate corresponding to the sample of galaxies you can look at. In an 8-meter telescope, you can do this to within about 10 megaparsecs, where for a sample you can look at it with one hemisphere, you can get a rate of about 1 supernova per year. It's still slow. To get a sort of more or less good result, you have to do this for 10 years. So it is a project best done with tenure. But it's feasible. Okay? Why not look for the associated transients? Well, the curious thing is despite the abysmal failure of supernova theorists to ever actually blow anything up, okay, there's very little study of what transient you should see when they don't blow up. And there's sort of more or less, here's sort of a diagram of what you would get in core collapse, right? There's explosion, which we're not going to worry about. No explosion. You could have a stalled shock, right, which then does something. You could have a direct collapse in which nothing happens. You could end up with a black hole in an extended quasi-spherical envelope, basically a black hole version of a Thorne-Zhitkov object. You could have a black hole in a disk. You could have an isolated black hole after it's all done. This case will be optically faint, right, just because even if the luminosity of a 10 solar mass black hole accreting at Eddington is not that different from a 10 solar mass black hole, where that one actually there's still a fair factor in that one. The thing is the temperature is so high that in the optical, at these distances, it would essentially vanish, even though the bulk luminosity is the same. This one would sort of be the most problematic, is because if you can use the remaining envelope basically as a transformer to transform the accretion disk luminosity back into optical photons, okay, then that would be the easiest case to have a black hole formation and hide it. We refer to these guys as zombie stars, but it's really sort of a black hole version of a Thorne-Zitkov object, and it should be fairly wildly unstable. Associated with this Lovegrove and Woolsey or Nadezhdan process, there is a transient, which I'll show you. I'll just show you a picture in a second. Woolsey and Hager have looked at this, and there are some stars whose density distribution is such that even with modest rotation, you really will literally get a prompt collapse. If the shock fails, the whole star just goes in on a dynamical time. If the whole thing doesn't go back, Kashiyama and Quattart recently were looking at this, and so at least in their model, most of the material would fall in relatively quickly, and there would be a relatively short but luminous optical transient associated with it, lasting for a week or two. Okay. But basically is you don't know what to look for, so you can't really premise the looking for on the transient, and so that's why we sort of look at presence of star to absence of star, and then go back and worry about what happened in between. Okay, so here, for example, is what you would get in this Lovegrove and Woolsey, is basically the hydrogen envelope drifts away at not very fast, a couple hundred kilometers per second. It powers a transient that lasts sort of a year at about 1 million solar luminosities, and the source of power is basically the recombination of the hydrogen in the envelope. It's basically just powered by the recombination energy. And so you get a short breakout spike, which in Woolsey's simulations is a little bit underestimated. Pirot studied this and says the spike should really end up sort of more about here. Okay, which would last about sort of a week. That would be very hard for current supernova surveys to find in any volume. Then you get this long transient of about 1 million solar luminosities. It's 3,000 or 4,000 Kelvin. And so basically it would look like a sort of M supergiant for a while. Then it fades out. And then at the very end, I was worried that you would never see this because the thing would make dust. And it turns out it only makes dust just as it's fading away. And it's one curious properties of its dust is it can solve the big grain problem that Bruce worried about at one point, because as it makes dust, it can make really whopping big dust grains approaching 1 centimeter in size if you really push the parameters, which is, I don't know, amusing at some level. Okay, so we actually then set out to do this using the Large Binocular Telescope. This is how we usually run it at night, right? We keep all the lights on and open it up like that, and this increases the sensitivity markedly. But it is a good art shot. Okay, and so basically we're looking at 27 nearby galaxies, which you can see from the north. They are everyone's favorite astrophotography targets. Okay, it is the Whirlpool, it is M81, it is M101. Okay, it's basically anything you could look at with a small telescope and go ooh and ah, because they have to be that close in order to collect enough photons from an individual star. Okay? So it has an actual supernova rate about 1 per year, and so if the failed supernova rate is 10 to 30%, you're expecting a failed supernova every 3 to 10 years. So as I said, it is a project for someone who wants to be patient. We get UBVR imaging, and just to give you a sense of the sensitivity is roughly speaking, we get 1 count per solar luminosity. Okay, so for 100,000 solar luminosities in a typical epoch of data, we are talking tens of thousands to 100,000 counts from that star. Okay, that doesn't mean we can necessarily recognize that as a particular star, because this is ground-based imaging of distant galaxies, and so crowding is a problem. And so this is all done with difference imaging. What we are looking for is changes, okay, and then the crowding problem goes away. And basically, we look at everything that changes in luminosity by 10 to the 4 solar luminosities. And the origin of 10 to the 4 is here a sequence of models as a function of zero-age main sequence mass of how luminous stars should be at depth. So if you just look at the R band, here's 1,000, 10,000, 100,000. Okay, here is this most interesting range around 20 solar masses. Okay, here is 10,000. So very low mass progenitors. Okay, we will have trouble seeing very well. The ones we most think are likely to be dying, we get very, very good signal to noise on. Okay, at R band, you have horrible signal to noise on the things which lose all of their mass. Right, Wolf-Rayet stars are, of course, notoriously difficult for anyone to find. But because we go to U band, okay, we get some sensitivity going towards the more stripped stars because we can see quite luminous blue stars. But again, if you strip a star enough, it becomes essentially impossible to find in the optical, no matter ground-based optical, no matter what you do. So there's nothing, it's very hard to do anything about monitoring Wolf-Rayet stars at 5 megaparsecs. Okay, so you do this. So we've done 3 years in Jill Gerke's thesis. And here are the sorts of false positives you get. The biggest source of annoying false positives is real stars which haven't gone away but just subtract badly. And they like to produce these bilobe residuals. So what you're going to see is in difference imaging, you have what's called the reference image. So you take all of your best images and average them together. And then you measure changes relative to this average image. Okay? You can take all of the residuals you have relative to that image and basically make a RMS image of the variability of the galaxy. So it's basically the RMS image of the variability in a galaxy. And in this case, for this bright star, you get these bilobed structures. Okay? Then here's what this star looked like at the first image. Okay? Then here are the residuals when you subtract in 2008, 2009, 10, 11, all the way up to 2013. And there's what it looks like in the last image. So if you go looking for stars that are varied by 10,000 solar luminosities, this very much more luminous star just has residuals that trigger that criteria. And so it's clearly there at the start, it's clearly there at the end, and then you're just wasting your time looking at residuals. That's by far the most common sort of initial false positive. No, it's unlikely proper motion. We will eventually have some proper motion objects, but for high proper motion objects, we're just not covering enough sky for there to be very many of them. It's because the total area of the survey is in the end not even, is only a square degree or so. So there are probably some in there, but I haven't gone looking for them. But there are too many of them for that to be the typical explanation. Bigger than an asteroid. So, right? Those are pretty rare. The most common ones are just variable stars where you catch them at their maximum, okay? End the survey period at a minimum. You say this changed by 10,000 solar luminosities, and then you just have to figure out it's a variable star rather than a vanishing star. And so these are just sort of two examples of that. All right. You do have examples of real dying stars. So here is supernova 2011 DH, which was in the whirlpool. And we've done this so that the reference image is comprised only of images taken before the supernova. Okay? And so basically, that's the average image of the star before it exploded. Then it has an RMS because it did vanish, so it looks like it's variable. Okay? So there's what it looks like in the first epoch. And then here are the residuals. And if you squint, I'll show you a better picture. Is the star was actually fading in the last few years before it died by a couple %. And unfortunately, Paul Martini deeply failed us by failing to have good weather the day before the supernova. We almost got an image of the galaxy the day before the supernova, which would have been kind of cool. So I've blamed Paul Martini for not better controlling the weather ever since. And then it goes away. And in this case, because we put the star in the initial image, the going away, you see the star appear as a negative. Okay, so this here is the star appearing as a negative. That is the photometry, essentially, of the progenitor. In terms of studying it as a progenitor, we have something like well over 100,000 counts to do photometry of the progenitor in UBVR bands. And so basically, we can do photometry of progenitor stars, which is basically calibration limited rather than counts limited. Okay, and so then the supernova was here. So this one was a roughly 100,000 solar luminosity star. It was somewhere between about 13 and 17 solar masses in recent analyses. It was a yellow supergiant. That is believed to do because it probably was in a mass transfer binary in the current models. Okay. So here's the sort of variability. The best is at R band. So here it is sort of 3 years before, going down to. We did actually observe it like 1 month before it exploded. And it faded by about 0.04 mag per year. Okay, it's less clear. We have best signal to noise in R, particularly for a star, which is relatively cool. Okay. If you want to have fun, you can say, it's 5 epochs. You can try to fit this with a binary model, just taking the parameters from the people who had the binary model. And you can also explain this variability as the binary model taken from the literature looked at cos I of about 0.2 or less. Now, clearly, you're not going to believe this, because if I now allow it to vary with time, I have no information on the inclination. But for example, if this had happened in M81, and we have 40 epochs for a star that blows up in M81, and so we actually will be able to probe things like the binarity of the progenitors much better. OK, and we're left with this guy, which for the sake of the HST proposal, we called NGC 6946 BH1. OK, and so here's what it looked like. So basically let's just look at the differences. This is set up so that the average is the average after the event. So it's set up to be not present in the initial reference image. Okay, so here's what is in the first image. Okay, then it actually has a transient in late 2008, early 2009. It brightened from about low 100,000s to about 1 million solar luminosities, and then it has vanished, and there is no source there as of 2 weeks ago. So it has basically not been seen for over 6 years. Okay. The transient is roughly consistent with what you might expect from Lovegrove and Woosley, but without nearly enough points to make that a convincing, fully convincing case. It is the amount it got brightened by, and the duration is not inconsistent. Okay. It is, however, exactly in the place where I've been advertising you should look. There is pre-existing HST data, and if you no, we have too many epochs. Well, plus, it's a 200,000 solar luminosity source before the explosion, so it can't be a nova. So you can track it back in CFHT data at that brightness to 2002. So yeah, it really can't be a nova. The other thing we do, which I didn't say, is we don't pick things based on the first epoch. We start with the second epoch explicitly to gate out novae. That basically something which is very bright in the first epoch you might call a candidate, but because it vanishes by the second epoch, but that's exactly what a nova will do. But generally on the time scale of our epochs is by the second epoch you couldn't see a nova, or you'd see something else. But if you say it has to be bright in the first 2 epochs, then basically you won't have any novae. We see plenty of novae. We just don't have well enough sampled light curves to bother saying much about them. So this is what it looks like in HST in 2007. It has several bands. And if you do standard fits, it was a red supergiant. It has a luminosity of about 200,000 solar luminosities. If you run that through the Padua isochrones at time of death, it was about an 18 to 25 solar mass star. So that looks promising. The next steps, which are sort of in process, 'tis the season to do proposals, is to first of all get HST to see that it's vanished. One thing you should be paranoid about, channeling one's inner Bruce Drain or equivalent, is that the other way you can make a star vanish is to obscure it. And so you have to worry about circumstellar extinction. In general, on these sorts of time scales, it's very hard to obscure something with cold dust, just because it's very hard to get things far enough away for the dust to be cold. And so in general, warm Spitzer is reasonably good because the dust temperatures are going to remain high enough to be picked up in warm Spitzer. It doesn't look like you can hide something this luminous in existing data. You can also go looking for X-rays. So in a not crazy length Chandra observation, you can get down to about 5% of Eddington. The problem is that while finding a new X-ray source would be pretty definitive, it's not clear that not finding an X-ray source is is not definitive in the other direction. Okay, so this is the real problem now. Is in some sense, if you back up and say, let's throw away the entire first half of this talk. What has this clown at the front of the room done? He's done the world's biggest survey for massive stars operating in a weird way, right? And he's found a star that has done something in a weird way, and he's advertising that it's a candidate for being a formation of a black hole in a failed supernovae. Okay. The problem is that our understanding of all the ways massive stars can behave badly is, shall we say, incomplete. And so the challenge is exactly how do you now prove that this is the correct answer? I mean, the best we can do, modulo the X-rays, you don't really expect any radio. That's sort of hopeless. The best we can do is we can say that this was a luminous star that existed for, say, a decade, okay, in archival data. It's had some sort of modest transient. Right? And then we can sort of keep saying is forevermore it is not there. Okay? And you'd really like to go with JWST, because JWST is the thing that can really nail basically all possibilities of dust. Warm Spitzer can't because it's warm Spitzer. And so that's sort of the remaining challenge. If you ask, are they completely crazy to have found this? Well, if you turn this into a rate, okay, here is the implied PDF for the limits on the rate. Okay, the answer is that the best fit is that it is consistent with a core collapse rate of 30%. Okay, and so it is not at all crazy given the prior story that we would have found one. Okay, if you say, it just ain't, right? Then you sort of get that, and you say that the failure rate has to be less than 40%. So basically, we haven't run the survey long enough to really strongly rule out this possibility. Okay, This enables other things. I think I should finish up, but you can sort of do non-crazy science as well. So for example, we have 81 long period Cepheids in NGC 4258, the Maser distance galaxy. We can do Cepheids at using 10% of the HST time that the Key project used per Cepheid. That basically you find them and phase them from the ground, and then you just calibrate them from space. And that's some issues, interesting issues in this age of dichotomy between some CMB and BAO estimates of the Hubble constant and essentially Cepheid supernova-based estimates of the Hubble constant. So let me just more or less finish there. We certainly have a candidate. The challenge, I think it's completely reasonable, is the challenge is to convince anyone. We're going to continue this for at least 10 years. We actually have almost twice as much data already. And so the next student will start doing the next analysis now. LSST, I should say, is not terribly helpful here. While the southern hemisphere is better for studying the galactic plane, the northern hemisphere is better for studying nearby star formation. So the LSST would only add 50% more supernova rate. And also you would have to do it as a dedicated sub-survey. LSST is a tiny telescope compared to the LBT. And if you co-added an entire year of standard LSST survey images, it is less than one of our epochs with LBT. So you could do it as a dedicated sub-survey. As I said, JWST is essential follow-up for protection against hiding with coal dust. And if you really want to expand the survey, you could do it with WFIRST. WFIRST could do this to 30 megaparsecs instead of 10 megaparsecs. And the real challenge here remains is no matter where you are with the candidates, the fundamental challenge is with a ground-based telescope, you could only do this in a sample with a supernova rate of 1 per year. And that makes it hard, right? But hard but doable. But if you want to do it in a short time, you wanted to do it with a supernova rate of 10 per year. And then in terms of rates, it becomes much easier. And so I'll stop there.